students. Today we are going to discuss about electronics and communications. Introduction of this electronics. You already know we use all daily life in electronics. That is a part of our life. All gadgets like mobile phones, computer, television, musical system, all are work on the principle of electronics. You already know. And communication system and medical diagnosis and treatments, even handling money through ATMs. All are this electronics applications. And microwave oven, air conditioners, all are these electronic applications. Then evolution of electronics. Electronics begin with the invention of vacuum tube, that is vacuum diodes, in 1897, and led to the introduction of tetrode and pentode tubes. And then nowadays the invention of transistor, that is bipolar junction transistor, in 1948. Then it is emergence of germanium and silicon semiconductor material made this transistor gain popularity, in turn its application in different electronical circuits. Then nowadays we use the invention of the integrated circuits. So all electronics kits are used this integrated circuits, that is ICs, digital integrated circuits, IC developments that enhance the architectures of computers. Then you know the first computer is this type, the second one this one, and third the laptop, and this one is a palm laptop. The first this palm laptop is 0.3 mm on each side. So this one is a room type computer, room fully occupied the room. But this one is the computer, then laptop, then palm. So the electronics is a branch of physics. And the behavior of movement of electrons and holes in a semiconductor, electrons and ions in vacuum or gas. Electronics deals with electrical circuits that involve active components such as transistor, diodes, integrated circuits, and sensors associated with the passive component like resistor, inductors, capacitors, and transformers. Okay, we deals the semiconductor device, that is like a PN junction diodes, bipolar junction transistor, and logic gates. First we see the energy band diagram of solids. Isolated atoms, that means a single atom, its electronic energy levels were widely separated. That means you already know there is a K cell, L cell, M cell. So that is a single electron. So this is a electrons levels. The atoms are closely spaced, and hence the electrons in the outermost energy levels of nearby atoms influence each other. Then valence electrons in an atom are responsible for the bonding nature. So consider an atom with one electron in the outermost orbit. So two atoms brought near, what happened? It bonding together. So you know that is the unoccupied orbits of each atom will also split up to split. So the electrons have the choice of choosing any one of the orbitals as the energy of both the orbitals in the same. You come when the third atom of some element is brought to this system, the valence orbitals of all the three atoms are split into three. So and fourth atom, so there is also come into the four atoms are split into 4. So unoccupied orbitals also will split into 4. So it is in a reality a solid is made up of millions of atoms. So the valence orbitals and unoccupied orbitals are split according to the number of atoms. So that levels are called a band. So the band of very large number of closely spaced energy levels in very small energy range is known as energy band. Okay, mark it. This one, the band of energy. This not a you write this. The band of energy, very large number of closely spaced energy levels in a very small energy range is known as energy band. The energy band formed due to the valence orbital is called valence band. This is also 2 mark. And conduction. What is conduction band? That is a conduction band is the due to the unoccupied orbitals to which electrons can jump when energized is called the conduction band. And the valence band and conduction band between a small gap, that is called the forbidden energy gap. The energy gap between valence band and conduction band is called the forbidden energy gap. This one is forbidden energy gap. This is the conduction band and this one is valence band. This is the forbidden energy gap. So this one insulator have energy band. This is a 6 electron volt. This is a conduction band. Conduction band up to this one is a conduction band. This one a valence band. So it is overlap with each other. So energy band is no. It means the electrons travel with the valence band and conduction band easy. It is loosely bounded. And this one is the semiconductors. So the forbidden energy gap is 1 electron volt for semiconductors. So in the conducting band, the free electrons, that is in green colors. In the valence band, this white color is a holes. The electrons go to the conduction band, so it creates a holes. So forbidden energy gap Eg equal to Ec minus Ev. So the potential energy decreases, indicating the electrons in the orbital closer to the nucleus are born with large potential energy. Hence, the electrons closer to the nuclei require a lot of energy to be excited. So you already know in excited state, the electrons go to excited state, ground state to excited state. It need a energy. So energy is much need for close to the nucleus of electrons. So the electrons in the valence band are loosely bound to the nucleus and can be easily excited to become free electrons. So there is classification of materials. That is, you already know, there is insulators, conductors and semiconductors. Then insulators, the energy band structure, you already know, that is energy band is very large in the case of insulator. For a glass, it is a 10 electron volt. And normally the insulator have 6 electron volt, and its range of resistivity is 10 power 11 to 10 power 19 ohm meter, and the electrical conduction is not possible as the free electrons are not available for conduction. Hence this material is called insulator. Okay, it is a 2 mark. What is insulator? The electrical conduction, mark this one. Up to this one. Okay. Next, conductors. Valence band and conduction band overlap. So electrons can move freely into the conduction band. This one. This is a conductor, it is overlap. And it's the free electrons move easily to the conduction band. And its resistivity is 10 power minus 2 ohm meter and 10 power minus 8 ohm meter. So even a low temperature, it will conduct the current. Next one is a semiconductor. So its semiconductor energy gap is less than 3 electron volt between the valence band and conduction band. So finite temperature thermal agitations in the solid can break the covalent bond between the atoms. So this releases some electrons from valence band to conduction band. Since free electrons are small in number, the conductivity of semiconductor is not as high as that of conductors. Then resistivity is 10 power minus ohm meter to 10 power 6 ohm meter. Semiconductor electron in the valence band are bond electrons which cannot move, hence they cannot contribute for conduction. Some energy given to this semiconductor, the electrons move valence band to conduction band. It conducts the current. So for the semiconductor material, some semiconductor material, that is silicon and germanium, and its energy gap is silicon is 1.1 electron volt and germanium is 0.7 electron volt. And types of semiconductors, there is two types, that is eccentric semiconductor and eccentric semiconductor. In the semiconductor in its pure form without any impurity is called an intrinsic semiconductor. Mark this one is a 2 mark. It is here impurity means presence of any other foreign atom in the crystal lattice. In the case, this one. This is covalent band. This one is a valence band. That is valence electron, covalent bond. These are all valence electrons in this type. These are all valence electrons. A small in temperature is sufficient enough to break some of the covalent bonds and release the electrons free from the lattice. As a result, some states in the valence band become empty and some number of states in the conduction band will be occupied by electrons. So this one is occupied conduction band. In the valence band, electrons go to the conduction band, this one. So the electrons move to this conduction band, so small holes are present. This green are electrons, this one is the holes. Then holes are deficiency of electrons. They are treated to possess positive charges. Electrons and holes are the two charge carriers in semiconductors. So in the case of semiconductor, intrinsic semiconductor, the number of electrons in the conduction band is equal to the number of holes in the valence band. Okay, you underline this one. In the semiconductor material, the conduction band, holes and valence band, that's all equal. Number of holes and electrons are equal. Okay, conduction, number of electrons in conduction band, number of holes in valence band are equal. So the corresponding currents are IE and IH, hole current and electron current. So the total current I is equal to IE plus IH. So definition for hole is when an electron is excited, covalent bond is broken. Now octet rule will not be satisfied. Thus each excited electron needs a valency to complete bonding. This deficiency of electron is termed as a hole. Then the intrinsic carrier concentration is the number of electrons in the conduction band or the number of holes in the valence band in an intrinsic semiconductor. Then eccentric semiconductor is not a purify. It means adding some impurities because to increase the carrier concentrations. So the process of adding impurities to the intrinsic semiconductor is called doping. So this is a 2 mark. What is eccentric semiconductor? For electrical conductivity, the impurity is added to the intrinsic semiconductor is known as eccentric semiconductor. So the impurity adding atoms are called dopants. In order to added impurity is 100 ppm. It is a 1 mark. So underline this one. ppm means parts per million. So on the basis of the type of impurity added, eccentric semiconductors are classified into 2 types, that is p-type semiconductor, n-type semiconductor. N-type semiconductor is obtained by doping a pure silicon or germanium crystal with pentavalent impurity atoms. That is fifth group of periodic table. Okay, the pentavalent atom is a phosphorus, arsenic and antimony and so on. Okay, the dopant has 5 valence electrons. So it is a 5 valence electron. This is pentavalence. So this impurity added. Pentavalent is a impurity. The phosphorus is added. So a small number of impurities are added. So the into the silicon material. So what happened? The phosphorus surrounding the silicons. So it is a 5. It's a valence are 5. So it bonding 4 electron bonding. One is a free electrons. The fifth one is a free electron. So during the process of doping, a few of the silicon atoms are replaced by pentavalent. Okay, these electrons are moving and it is impact with other electrons. So the electrons come out the bonding and it fill the fifth electron is fill this holes. So in the conduction band, the donor energy levels below this conduction band, level is created that is called a donor energy levels. So the energy level of loosely attached fifth electron from the dopant is found just below the conduction band edge. That is called donor energy level. At room temperature, these electrons can easily move to the conduction band with the absorption of thermal energy. Okay, this one. This is a donor energy level. So electrons from dopants. Thermally generated hole. So an external electric field can set free the loosely bound electrons and lead to conduction. It is important to note that the energy required for an electron to jump from the valence band to the conduction band is an intrinsic semiconductor is 0.7 electron volt for germanium and 1.1 electron volt for silicon, while the energy required to set for a donor electron is only 0.01 electron volt for germanium and 0.05 electron volt for silicon. You underline this one. This is a 1 mark. So this pentavalent impurity atoms donate electrons to the conduction band and are called donor impurities. Then each impurity atom provides one extra electron to the conduction band. In addition to the thermally generated electron, these thermally generated electrons leave holes in valence band. Hence, the majority charge carriers of N-type semiconductor are electrons and minority carriers are holes. So, you memory this one. N-type has majority charge carrier is electron and holes are minority charge carriers. So this pentavalent impurity is called N-type semiconductor. Next one is a P-type semiconductor. It is a trivalent impurity atoms, that is third group of periodic table, such as boron, aluminium, gallium and indium are added to the silicon or germanium crystals. So the dopant with 3 valence electrons form 3 covalent bonds. One covalent bond is a 3 bond completed. The remaining one is incompleted with 1 electrons. So this electron valency presence in the fourth covalent bond is represented as a hole. Okay, so in this case, this one hole. So this electrons jumps to neighboring electrons or jumps to the fill up this hole, and the hole found the neighboring bond. So it travels, these holes are travel and electrons are travels. So in the p-type semiconductors, the majority charge carrier is holes and minority charge carrier is electrons. So in the case the valence band near, that is upper side, a closed valence band closely near the acceptor energy levels are created. So the energy level of the hole created by each impurity atom is just above the valence band and is called acceptor energy level. So acceptor atom, there will be a hole in valence band. This is an addition to the hole left by the thermally generated electrons. So such an eccentric semiconductor holes are the majority charge carriers and minority carriers are electrons. This is a p-type semiconductors.